Hi all, welcome to 15th lecture of this course on Unconstrained Optimization. And today we'll discuss about variations of classical Newton methods, basically trust region methods and Quasi-Newton methods. We'll first conclude our discussion on classical Newton method and then go on to see some modifications that try to overcome disadvantages of classical Newton methods, and we'll also analyze these algorithms. Before starting the lecture, let's just recall what we studied in our previous lecture. So we studied classical Newton method. So in this classical Newton method, uh, uh, the update differs from steepest descent method in a way that uh, it does um, it does use the gradient in the descent direction, but it changes its direction by multiplying it through HK inverse, which is the Hessian matrix inverse. So the descent direction is minus HK inverse GK, and the step length is 1. There is no line search in classical Newton's method. If we look at it in the algorithmic form, then we first initialize x naught, the initial point, and the epsilon, which is used for stopping conditions, and we set the iterate to 0. We start the loop where condition is that gradient should be greater than epsilon, and we first set the descent direction by minus HK inverse. We calculate HK at each point, GK at each point, and then set the descent direction to minus HK inverse GK. We set the step length, and the rest is as 1, and the rest is straightforward. HK plus 1 is equal to xk plus alpha k dnk, and we update the iterate as well. We end the loop when the stopping condition dissatisfies, and we get the output as x star xk, which is the stationary point of fx. Now there is one very big advantage of Newton's method over steepest descent method, that the minimum of the strictly convex quadratic function. So if you have a quadratic function which is strictly convex, that is, it has one and only one local minima, which is also a global minima, and which has a invertible Hessian, so its Hessian matrix should be invertible, then we attain the solution in one iteration. So you start from any starting point. So let's say this is a convex function, and you start from any initial point. If these conditions are satisfied, you'll reach the minimum in one step. If you use exact line search, of course, so you reach the minimum in one step. This is an advantage, as we saw for steepest descent method. It might take a lot of steps depending upon which initial condition you are taking. There are several disadvantages of Newton's method as well that we will discuss now. We also discussed it in the last class. So the first is the algorithm needs second order info, which might be difficult to get. So at each step, as you saw, you need HK inverse. So first you have to calculate HK, which itself is a task, and then you have to calculate its inverse, which increases the computational effort. So computational effort is very high. Also the storage space is requirement is very high. You can see O(n) cube computational effort and O(n) square storage space requirement, which is much more higher than the steepest descent method. Okay. Also, there is no guarantee that dnk is a descent direction, because you multiply HK inverse to GK, and there is no check whether this is negative only when this is a descent direction if HK is a positive definite matrix. So there is no check whether HK is a positive definite matrix or not in this algorithm, and if it is not positive definite, this might not and if it is a negative definite matrix, let's say, and there is no check, then this direction becomes an ascent direction, which is opposite of what we want. Also because HK is not in our hands, it can be very close to singular matrices and might lead to numerical difficulties while calculating the inverse of the matrices, which is itself a numerical problem. Also, we saw that we set alpha k equal to 1. There is no line search. So even though you might get a descent direction, there is no guarantee that the function value will decrease. It might happen that at alpha k equal to 1, the function value might increase. That is one disadvantage. And the sensitivity to initial point is very, very high. So let's say it happens that for some initial points, the algorithm may diverge. So for some initial point, the algorithm may diverge, it might not converge. So that is one of the major problem of Newton's algorithm. So to study about this sensitivity to and divergence of Newton methods, there is a definition on locally convergent optimization algorithm. So what are these? So these are algorithms. These are optimization algorithms, which, for example, you have a multiple solution in a function. For every solution x star, there exists a delta, a positive number delta, such that if you choose your initial point within the ball of radius delta around x star, then your algorithm converges to x star. This is locally convergent. Basically, it is saying that if you choose for these kinds of algorithm, if you choose your initial point sufficiently close to your optimal point, then your optimization algorithm will converge, otherwise it won't. And classical Newton algorithm is a locally convergent algorithm. So you need to choose your initial point sufficiently close to your optimal point. This point we did not prove, will not give the proof of this, they will present to you as a fact, but there is a proof of this point. This is that classical Newton algorithm is locally convergent is written in some informal way. So we'll just write a theorem first. We'll end the recall from previous lecture here, and we'll start the next lecture now. In the theorem, we'll state this fact itself in a more formal way, even though we will not derive it. We will not derive that theorem, but that will help us understand that for a classical Newton algorithm, you need to choose a point sufficiently close to your optimal point. So let's see the theorem. Again, I'll first write the theorem and then I'll explain it. Let f from R to R and f belongs to some function whose gradient is also continuous, double derivative is also continuous and differentiable. That the C3 means that. Please note here f is from a single variable input. So domain of f is real numbers. So let x star belong to R be such that gx star equal to 0 and g prime x star is greater than 0. So this is the sign that x star is a local minimum of this function. Then provided x naught is sufficiently close to x star, the sequence xk generated by classical Newton algorithm converges to x star within order of convergence 2. So basically what this is saying, so let's say we have a real valued function from R to R, and let x star be its local minima. Then if x naught, the initial point, is sufficiently close to x star, then the algorithm will converge within order of convergence 2. So the convergence is fast given that it is sufficiently close to x star. The problem with this with classical Newton according to this theorem is initialization of x naught requires knowledge of x star. So basically what this is saying is to ensure that the algorithm converge, to choose such a point x naught, you already should know x star, where the x star lies, which is like counterintuitive. How, if you already know x star, why are you anyways optimizing? So this is the problem with Newton's algorithm. So to solve these various disadvantages of Newton algorithm, people have done modifications to Newton method which solves many of the disadvantages that we discussed. We'll discuss these algorithms now. So now let's look at the modified Newton method. So modified Newton method. So what are the modifications that we are looking at? So in Newton method, given xk and dk, dnk, in the descent direction is given as dnk is given as minus hk inverse gk. So the modification that we do in this modified Newton method is fix some constant delta greater than 0. So fix some constant delta greater than 0 and find the smallest real number psi r greater than equal to 0 such that so we try to make a new eigenvalue. So we try to make a new matrix that we can multiply with gradient, right, such that the smallest eigenvalue of the matrix hk plus xi r I is greater than delta. Okay, so we try to, these are the 2 points, fix some delta greater than equal to 0 and find the smallest psi r greater than equal to 0 such that the smallest eigenvalue of this matrix is greater than delta. So what does this do? What does this modification like? How does it remove the disadvantages in the classical Newton method? So we had two problems, if you remember. Like two of them we just two of the many we discussed just now. So in classical Newton method, HK can be negative definite, right? So if HK is negative definite, DNK, which is given by minus HK inverse GK, might be ascent direction. Alright, and this is not what we want. So this was one of the disadvantages of classical Newton method. And HK can be very can be close to singular matrices. So it can be a matrix which is not exactly singular matrix but very close. So eigenvalues are really small. So this modification solves this problem so that we choose delta greater than equal to 0, and if smallest eigenvalue value is greater than delta, which means that all the eigenvalues are positive, and we can choose if when all the eigenvalues are positive, which means HK plus xi xi r I is positive definite because all the eigenvalues are greater than 0. Second thing is we can choose delta to be significantly big so that HK plus xi r I is far from singular matrices. Alright, so this we can do. We can choose delta in such a way. So these two problems are solved using this modified Newton method. So now this dk given by minus HK plus xi r I inverse GK is a descent direction. Alright, so it always is a descent direction, and there will be no numerical difficulties in calculating its inverse because it is far from singular matrix. There is one more modification that we do, which is quite logical, that we do line search as well. So given xk and dk given by hk plus xi xi I inverse GK use line search techniques to determine alpha k and xk plus 1. Alright, so we use in classical Newton method alpha k is always 1, but that also that does not that does not guarantee if fk plus 1 is smaller than fk, right? But this, because we are doing line search, now we are guaranteeing this is true. So these three problems it solves, this modified Newton algorithm. So xk plus 1 is given by xk plus alpha k dot dk, where dk is given by uh, minus of hk plus xi ri inverse gk, and alpha is given from line search algorithm, either exact line search or inexact line search. This ensures that fk plus 1 is less than fk. Now one of the problem of this modified algorithm is if xi k, sorry, this is always k, I'd say it's xi r but it's k, my apologies. This is xi k. So basically xi k is the smallest eigenvalue a number which when multiplied by I and added to hk gives increases the smallest eigenvalue of h of this matrix greater than delta, right? So now this number xi k depends upon hk. Okay, what is hk? So if hk is large or xi k is large, then dk is close to steepest descent direction, because remember, steepest descent direction is minus gk, where uh, uh, and so general algorithm had ak gk, steepest descent chose ak to be I, and classical Newton method chose ak to be hk inverse, and this modified has chosen ak to be hk plus xi k I inverse. So you can see that if xi k is very very large, then this is closer to I, the component of I increases, and hence this becomes closer and goes closer and closer to steepest descent direction, this method. So this is what this point is saying, that if xi k is large, dk is close to steepest descent direction, and the fast convergence is lost. So fast convergence is lost. But yeah, but it ensures convergence, so that's the benefit. Um, so it has global convergence properties. Yeah, so it does converge, so it won't, the descent direction, that the formula that we are using will never become an ascent direction, so it guarantees some convergence, and from any initial point. So we saw in classical Newton method that it has to be, the initial point has to be selected very close to the optimal point, but in modified Newton algorithm it will converge from any point. So let's look at this algorithm, look at this matter in algorithmic form. So modified Newton algorithm. Right, so modified Newton algorithm. So first, like in every algorithm, we initialize. So we initialize x naught, epsilon, and one more thing we have initialized delta, and we set the iterate equal to 0. Alright. Now while this stopping condition is not satisfied, set the gradient, the norm of the gradient is greater than epsilon, the loop keeps on moving, going on, and the first step is, what is this first step? So find the smallest xi k greater than equal to 0 such that the smallest eigenvalue of hk plus xi ki is greater than delta. So this in itself is a problem to be solved. So you have to find such psi k such that the smallest eigenvalue of this matrix is greater than the given scalar delta. Now once you get that, set dk equal to minus hk plus xi ki inverse minus gk. So this is the descent direction. In C, you do line search. So find alpha k greater than 0 along dk such that. So what are the two conditions that need to be satisfied? fxk plus 1 is less than fxk. This is necessary, and Armijo and Wolf or Armijo and Goldstein condition are satisfied. So alpha k satisfies Armijo Wolf or Armijo Goldstein condition. So you have found both direction and the step length. Now you just update and do the update step, that is xk plus 1 equal to xk plus alpha k dk, and update the iterate k plus 1. We end the loop here, and like always the output is x star equal to x star equal to xk, the stationary point of x. Alright, so this is the algorithm, modified Newton algorithm. So it has 3 steps. One, you have to calculate 3 extra steps. First we have to calculate xi k, which makes this matrix smallest eigenvalue greater than delta. Then we set the descent direction like this, and then we also do a line search to find the step length, which was not in the case of classical Newton method. It turns out if you use modified Newton's algorithm, there are some convergence guarantees. So modified Newton algorithm has global convergence properties. And has order of convergence equal to 2. So what this statement says that it has global convergence properties means you need not be near the optimal point for it to converge. It would converge from any initial point, and it also converges faster. So it has at best the order of convergence of 2. It goes down if xi k obtained is very large, because the direction moves closer and closer to steepest descent direction, but in general order of convergence is faster than steepest descent. Now let us look at some other modifications that we can make in classical Newton algorithm apart from that we saw above. So next modification or next algorithm is trust region based algorithms. Trust region methods. So before discussing what the algorithm is, what kind of problem it solves, let's discuss motivation of trust region methods. So we'll see what motivated this modification, and then we'll see how is it useful. Now consider the problem minimization of fx given x belonging to Rn. So this is the problem we want to solve, and the assumptions that we saw earlier also, that f belongs to C2 and f is bounded below Now Newton method uses quadratic approximation. So it uses quadratic approximation of f at a point given at a given point xk. So basically fx is given by f qkx, and it's fxk plus gk transpose x minus xk plus half x minus xk transpose hk x minus xk. I'll just shift it a little bit so that it fits in a single line. So this is the quadratic approximation that the Newton method uses, and xk plus 1 is the minimizer of fqkx. Alright, so in Newton method what we do, we take this quadratic approximation and find the minimum point, which is, and take that as xk plus 1. In the form, the motivation of trust region methods came when someone asks the question, what is the region of trust? So, what is the region of trust? In which the approximation is reliable. So people ask the question, let's say I have a quadratic function, uh, 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 let's say I have some function fx and I am at point xk, and I approximate the function with some quadratic approximation. Now what is the area of trust? So let's say this yellow region gives us a area where the quadratic approximation of the function is reliable. Beyond that, the error becomes big. So in Newton method, we try to find this point, the minimum point, but in trust region we restrict ourselves in this region of trust. Okay, so this is the motivation that through which people came up with this trust region based method. So let's see what trust region method is. So trust region method. So given delta k greater than 0, some real number delta k greater than 0, let the region of trust be omega k, where omega k is given by a set of x such that norm of xk, x minus xk or xk minus x, same thing, is less than equal to delta k. Alright, so it's basically a ball of radius delta k surrounding xk. This is the region of trust. Let's show it to you visually. Let's say this is some function. Alright, so, and this is its contour map. And this is the contour map of that function. Let's say we are at xk, and this is the quadratic function approximation of the given function at xk. Alright, so the region of trust is this circle. Let me draw a different circle. Alright, so region of trust is this circle centered at xk and whose radius is delta k. Alright, so this is the region of trust, and we try to find the minimum of the function inside this region of trust. Now what we do is we solve the following constraint. Solve the following constraint problem to get xk plus 1. That is minimization of fqkx such that x belonging to omega k. So for x belonging to omega k, so for all the x belonging to this circular region, we try to solve this constraint optimization problem. Now we haven't studied constraint optimization problem as of now, but this particular problem is easy to solve. Why? So basically what happens, because this is a quadratic function, so what we can do is find the unconstrained optimization of this using Newton's method. We'll get this point. Alright, we'll get this point in one iteration, right? Now if this point is outside if this point is outside the trust region, alright, so if this point is outside of trust region, then what we'll do is we'll draw a line from xk to this minimal point and see where it cuts this circle, which is easy point to solve. This will be the lowest point. You can see it visually also, and you can think about it that this will be the minimum point for this quadratic function. So this is, even though it's a constrained optimization problem, but this problem is easier to solve. Now once we get the solution xk plus 1, then this is how the algorithm will work. But there are two questions. There is one question that is still remaining, that how do we get omega k plus 1 from omega k or other things that we have? How to determine omega k plus 1, or should I say delta k plus 1. So if I have delta k plus 1, I know how to get omega k plus 1, but how do I calculate delta k plus 1? So it turns out there is an algorithm to predict these two. So let's look at that algorithm. So algorithm to determine delta k plus 1 and rk. We'll see what rk is. So here rk is basically a relative reduction in the values of functions. So we'll see what it is in a minute. So what in the algorithm, what we do, in the first step we are given, in the current iteration step, we are given delta k, we have been given xk, and we have calculated xk plus 1. All right, we have calculated this through solving that optimization problem that we saw, this problem, right? So we are given xk, delta k and xk plus 1. We calculate rk now. What is rk? Rk is the relative decrease in the value of the function, the ratio of real reduction in value of function to the to the reduction in value of the function which was approximated. So f xk minus f xk plus 1 divided by f q k xk minus f xk plus 1 q. Alright, so what this is doing is it's the ratio of actual function value, the difference of action function value in xk and xk plus 1 and the approximated function value at kth step. So here you can look this is kth approximation of x at both point xk and xk plus 1. So the ratio of this is this rk. So this is an important step. So once we have this rk, we see if what is the value of rk. So rk, if it is less than 0.25, if it is less than 0.25, which means that the difference of the approximated function and the real function is huge, is big, right? So we want to shrink the region of trust. So what we do, we reduce the value of delta k plus 1. So now the region of trust, we can reduce it. So these are just these are just parameters which, and 0.25 are just parameters which we can choose according to our own algorithm, but this is a generic way that I'm telling it to you. Now if rk is small, so basically this if condition says if rk is small, then there is that the actual function, the reduction in actual function is less compared to the reduction in approximated function. So what we do, we shrink the region of trust. Now else if rk is greater than 0.75, if it is greater than 0.75, then what we do, we increase the region of trust. So delta k plus 1 becomes 2 times delta k, and if it is in middle, then we are at nominally good position, so we do not change the region of trust, so it remains the same. So delta k plus 1 equal to delta k, right? And we end the if condition here. So for us the output is delta k and rk. Alright, so this is the algorithm that helps us calculate delta k and rk, basically the radius of the region of trust and the relative decrease in actual function value and the approximated function value. Now using this, how can we calculate or how can we optimize the function? So this is one of the algorithm that is used within the optimization algorithm. Now let us look at the original trust region based algorithm. So trust region based modified Newton algorithm. Let us look at it. So we first initialize all the values that need initialization. So initial point, epsilon, that is used for stopping condition, and this time we also need delta naught, the initial radius of region of trust, and then we also set the iterate to 0. Now we start the loop. Stopping condition is as usual, the norm of the gradient should be greater than epsilon. uh, and now the first step is finding the optimal xk plus 1. How do we find xk plus 1? So the first step is xk plus 1 equal to arg min such that x belonging to del omega k f q k x. So this is the approximate quadratic function, and we try to find the minimum of this function given x is in the trust region. Okay, so we already talked how we'll get this. So if the approximated function lowest value, sorry, if the optimal value of this quadratic function lies within the region of trust, then we just use this, we'll get get it in one single iteration using Newton's method. If not, then we'll join if not we'll join the line from xk to the optimal point, and the problem to this optimization is where the line intersects this circle. So there will be two possibilities. We saw already how to solve this problem. So we'll first solve for xk plus 1. Once we get the xk plus 1, we use the previous algorithm to determine delta k plus 1 and rk. Alright, so these two things we calculate, and now sometimes it may happen that the region, the rk might be less than 0, right? So if there's no restriction on the value of rk, so if it is less than 0, which means that even though the actual, I mean, it might happen that either the actual function value or the approximated function value might have increased. So the actual function value must have increased rather than decreasing. So this is not ideal. We don't want to go to the next point. So we reset xk plus 1 equal to xk. So let us understand this step properly. So rk is given as fk minus fk plus 1 upon fqk minus fqk plus 1. Now because we are doing a quadratic function, this will always be positive because we are xk plus 1 for a given function is always less than fxk. So we are for the approximate function, because it is reducing. But it can happen that the approximation is not good and the actual function value might be larger. So fk plus 1 is greater than fk in reality, and in approximation it is reducing. So rk can be negative. In that case, we do not, xk plus 1 is not a good point, so we do not want that point. So we reset xk plus 1 to xk. This is what we are doing here. So this is just a resetting to ensure that fxk is always monotonously decreasing. Alright, once this is done, we'll just update the iterate. We already updated xk plus 1, so that's done, and we'll end the loop. The output is as in all the algorithm x star is equal to xk, a stationary point of s. Stationary point of fx. Alright, so this is the algorithm. Now let us look at visually how the trust region thing works. How do we change the trust region? So let's say our initial trust region was delta k at this point, and alright, so let's say this is the initial trust region. This is xk and this is delta k, the radius. Now we try to find the next point. Let's say we get the point here. Alright, so xk plus 1. The way it works is, let's say this is the approximation and this is the minimum point, but we'll restrict it to our trust region, so we get xk plus 1 here. We now do that checking, what is rk, right? If it is less than 0.25, we'll take this sk plus 1, but we'll reduce the trust region, right? So now the trust region will be a smaller point. So the delta k will be reduced to delta k is reduced to 1/4, right? So the next trust region will be lesser, right? If it is greater than 0.75, we'll increase the region of trust, right? So we'll increase the region of trust around xk plus 1. Now let's say if it is less than 0. Okay, so what happens is we got this xk plus 1, but now what rk is less than 0, rk is also less than 0.25, right? So we'll reduce the region of trust here. We reduce the region of trust, this is delta k plus 1. And we update xk plus 1 such that xk is again the xk plus 1. This we saw, right? Because the approximation was not good and we are not reducing the value. fk plus 1 actually increased. That's why we go back to xk and reduce our region of trust. Alright, so this is how this algorithm works. I hope this visual understanding might have helped you a little bit. You can go back and read this algorithm again. I'll share the notes in the description. Now let us look at another modified Newton algorithm called Quasi-Newton methods, and it's very popular. So Quasi-Newton methods. Alright. So the basic idea of Quasi-Newton is as follows. So in Newton's method, the descent direction is given as hk inverse gk. This is the Newton's method. Alright. In Quasi-Newton method, the descent direction is given by minus of bk gk, and there is no inverse. And it turns out this Quasi-Newton algorithm is more computationally efficient. Computationally efficient. All right. So what is this BK matrix and how is it calculated? Let's look at that. So consider the problem of unconstrained optimization. Minimize fx where x belonging to Rn, where f is a real valued function from Rn to R, and f is continuously differentiable function. So this is what is required for Quasi-Newton method. For in Newton's method, we get this direction hk as follows. So for Newton's method, f belongs to C2 actually, and it is there is a quadratic approximation of fx which is given by fqx, okay, given by fxk plus g k transpose x minus xk plus half x minus xk transpose hk x minus xk. So this is the approximation of the quadratic approximation, and through this we find the minimum of this quadratic function, which turns out to be with alpha k equal to 1 and dnk equal to minus hk inverse gk. So for Quasi-Newton method, we change this quadratic this quadratic model slightly. So for Quasi-Newton, f is only required to be continuously differentiable. That is, it should belong to C1. And Quasi-Newton, for Quasi-Newton, we form a quadratic model as follows. So y k x is given by fxk plus gk transpose x minus xk plus half x minus xk transpose bk inverse x minus xk. So in place of hk, we have bk inverse here, and this bk is a symmetric positive definite matrix, and the Quasi-Newton direction is given by, as we have seen earlier, it is given by minus b of k gk. And because bk is positive, symmetric positive definite, implies this is a descent direction. All right. So this is how we ensure that for Quasi-Newton method, the direction in which we proceed is a descent direction, which is not the case for Newton method, as we have discussed earlier, that HK is symmetric but may not be positive definite. Okay, so please note HK is symmetric but may not be positive definite. Okay, so this is one of the drawbacks of Newton's method that we are trying to correct. So this is how the this is the theory of the Quasi-Newton method. So note here that I'll just copy this. So VK inverse is either as HK or its approximation. So we try to find BK with less computationally intensive task such that it is an approximation of HK or either it is HK itself. And the update step is given as same as in earlier algorithms, that is xk plus 1 equals xk plus alpha k d quasi Newton k, which is same as xk minus bk gk into alpha k. All right, so this is the algorithm. Now it poses several questions. So we do not know anything about bk, how bk is calculated. So let's write down all the questions that we need to answer to fully define this algorithm. So first question is how to calculate bk plus 1. So given xk plus 1, so we calculate, so given xk plus 1, gk gk plus 1 and bk. How to update bk to get a symmetric positive definite matrix bk plus 1. How do you get this matrix? So let's say you have been given all the so we have xk first. We calculate xk plus 1 through this formula, and we take some initial value of b naught, let's say, and we have bk. How do we calculate bk plus 1 from this information? That we have to figure out. Note there is an additional requirement, that is bk plus 1 should be symmetric positive definite. So that is also taken into consideration. That should also be taken into consideration when we are trying to update bk. The second question, natural question is is bk approximately equal to hk inverse? And if it is, how good is the approximation? So is it equal to HK inverse, and if it is, how good is if is it approximately equal to HK inverse? If it is, how good is the approximation that we want to answer? And are there any condition that we, so let's say, can bk plus 1 be any symmetric positive definite matrix, or does it need to satisfy certain condition? So are there any conditions that bk plus 1 should satisfy? All right, so these are the three questions that we'll answer one by one. So let's try to answer the first question first. So we have already seen this formula. I'll copy it again. Right, we'll keep it here. So this is the approximation, Quasi-Newton approximation into a quadratic function around xk, right? This is around xk. So now this is the approximation. We calculate xk plus 1 through this formula. Xk plus 1 equal to xk minus alpha k bk gk. All right, we get x plus 1. Now given xk plus 1, we construct a quadratic approximation of f at xk plus 1. So now we try to make a quadratic approximation of the function at xk plus 1, which will be similar to this at xk only. So which will be yk plus 1 x is given by f of xk plus 1 plus g of k plus 1 transpose x minus xk plus 1 plus half x minus xk plus 1 transpose bk plus 1 inverse. Let me just shift it into x minus xk plus 1. All right, so this is the quadratic approximation of the given function near around xk plus 1. So now what are some conditions that this quadratic so note that we have this k plus 1 is unknown. We have to find this. So this is unknown. Now what should be the relation between these two function definitions, these two approximations? Because x and xk plus xk and xk plus 1 are nearby points, we can assume that there is some requirement that these two functions should follow. All right, what can be those requirements? The gradient of y at k plus 1 of k plus 1 at xk plus 1 should be equal to the gradient of original function at xk plus 1. All right, and the gradient of this new function xk plus 1 at xk should be equal to gradient of f xk. This is a reasonable requirement. So we say that this function, if it is a good approximation of original function, then the gradient at xk plus 1 and xk should be equal to the respective gradients of the functions. Okay, so the first condition, that is this one, delta yk plus 1 xk plus 1 is nothing but gk plus 1, right? You can see this will go to, if you find the gradient, this will go to 0, this will become gk plus 1, and this will remain bk plus 1 inverse x minus xk plus 1. As soon as you put xk plus 1, this becomes 0. So yeah, so only gk plus 1 survives. On the other hand, for the gradient of the function itself will be gk plus 1, right? So this is LHS, and RHS is also gk plus 1 because it's the gradient itself, right? So this is what the value is. So this is always true. So the first condition is always true, right? Always true. Let's look at the second condition. All right, what will be the delta yk plus 1 yk? So delta yk plus 1 xk, sorry, this will be gk plus 1 plus bk plus 1 whole inverse x minus xk plus 1, and in place of x you'll put x. Okay, so this is the value and of left LHS. This is LHS, and RHS will be g of k, right? So basically it will be delta f of xk will be nothing but g of xk, which is equal to g of k, right? So these two should be equal. So gk plus 1 plus bk plus 1 inverse xk minus xk plus 1 is equal to gk, right? This converts to gk plus 1 minus gk. I bring it on this side and I send the whole to this side. So this will become bk plus 1 inverse xk plus 1 minus xk. All right, so this is the case. I multiply by bk plus 1 on both sides, then it will be, and I assume gamma k as gk plus 1 minus gk and delta k as xk plus 1 minus xk. So this becomes gamma k equal to bk plus 1 inverse delta k, right? If I multiply by bk plus 1 from both sides, then bk plus 1 gamma k equals to delta k. And this is called the Quasi-Newton condition. So this condition, the bk plus 1 should follow. So while updating b or the bk, the new bk plus 1 should follow this relation always. So this is the condition that should follow. This answers the third question that we asked, that are there any condition that bk plus 1 should follow? So this is that condition that it needs to follow. This is called Quasi-Newton condition. All right. Now let's analyze this condition a little bit. Okay, so the Quasi-Newton condition is nothing but bk plus 1 gamma k is equal to delta k, right? So please note the requirement of bk plus 1 is it should be symmetric and positive definite. It should be symmetric, positive definite. So from positive definite, if it is positive definite, bk plus 1 should be positive definite, right? Which means bk plus 1 gamma k. If we multiply gamma k transpose on both sides, because this needs to be positive definite, this has to be greater than 0 for all gamma k not equal to 0. Okay, so for all gamma k not equal to 0, this quantity has to be greater than 0. That's the requirement. Only then bk plus 1 will be a positive definite matrix, and only that is the valid bk matrix. Now let's say, while finding the step length, all right, so while finding alpha k, we use Wolff's condition. So from Wolff's condition, if we try to find alpha k through Wolff's condition for line search, what does the Wolff condition say? So Wolff condition says gk plus 1 transpose dk should be greater than equal to c2 times gk transpose dk. This is what the Wolff's condition say, and c2 belongs to c1 to 1. We can assume 0 to 1. It's the superset of that, and you can see here dk is not can be is the direction, the descent direction, right, at xk, which is equal to xk plus 1 minus xk, correct? So dk is actually equal to delta k. So if I subtract gk plus 1 dk from gk transpose dk from both sides, that is gk plus 1 transpose delta k minus gk transpose delta k from both sides, c2 gk transpose delta k minus gk transpose delta k. If I do this, this becomes gamma k transpose delta k greater than equal to minus 1 minus c2 gk transpose delta k. Now look at this, we have a negative sign, so this quantity, because c2 belongs to 0 to 1, is always greater than 0, right? Now remember, if g is g, remember that delta k is a descent direction, then gk transpose delta k will always be less than 0, right? And this is here is less than 0, minus negative, so this whole quantity is greater than 0, right? This whole quantity is greater than 0, which means if we use Wolff's condition to select the step length, then gamma k transpose delta k is always greater than 0, right? Which means there always exists a beta k plus 1 which is positive definite. So when Wolff's condition is satisfied, there exists a bk plus 1 which satisfies Quasi-Newton condition. Alright, so basically if you use Wolff's condition to find the step length, the new xk plus 1 will be such that, and the new bk, there will always exist a bk plus 1 matrix that will follow the Quasi-Newton condition and will be positive definite. Alright, now let's try to find how to calculate this bk plus 1. Alright, so let's see how many number of variables are there. So let's analyze it a bit. So you can see, because bk is a symmetric matrix, how many variables will it have? So let's say this is the matrix n cross n. Because it's a symmetric matrix, the number of independent variables will be all the diagonal elements, that is n, plus all the elements in the lower half triangle except the diagonal, which is how many are those? So n square minus n by 2, right? So this is the total number of elements. How much is this? So n minus 1 by 2 plus n, which gives us 2n plus n square minus n by 2, which is n plus 1 by 2. So these are the number of variables. So this is bk plus 1, remember. So if we have to find an n cross n symmetric matrix, then we have n plus 1 by 2 number of variables. Okay, let's just write it. I'll keep it here for your reference. All right. Okay. All right. So n plus 1 by 2 variables, because bk is symmetric. All right. Now, how many Quasi-Newton conditions do we have? So how many Quasi-Newton conditions we have? We have n equations. Quasi-Newton condition. How can we say that? So if you look, it is bk plus 1 gamma k is equal to delta k. So bk plus 1 is n cross n matrix, gamma k is n cross 1 vector, this is n cross 1. So basically we have n equations here, right? So yeah, and there is one more requirement, that is bk plus 1 should be positive definite, right? So there are conditions related to that also, which are n inequalities. Why n inequalities? Because bk plus 1 should be positive definite, which means all principal minors should be positive. All right, so all principal minors should be positive, which means we have n inequalities. This is the requirement for positive definiteness, please remember. So one thing that comes out as an observation is, so we have n equations, but we have more number of variables, a lot more, right? Even when we have n inequalities, the number of variables are still very huge compared to the equations. So number of variables is much larger than number of equations, which means there are more than one solution. So there are many bk plus 1 matrices possible. Okay, so there are many ways we can update, in which we can update bk plus 1, because there are several solutions. There is no unique solution here. So let's consider the most simple way of updating bk. So consider a simple way to update bk. All right. So the way we do it is, let alpha be some number, non-zero number. Let u be a vector from Rn, and u should not be a zero vector. Okay, then bk plus 1, if we take as bk plus alpha u transpose, if we take this, note that bk plus 1 is symmetric. This is given to us. This is symmetric positive definite, right? Alpha is some real number, and u transpose. What is u transpose? So let's see what is u transpose. Okay, u1 u2 un, and u1 u2 un. So this is u transpose. What is this equal to? u1 square, u1 u2 u1 u3 and so on, u1 un. What will be the column? u2 u1 u2 u2 square, u2 u3 and u2 un. Then this will be u3 u1 u3 u2 u3 square and so on. So you can see this value is equal to this value, this value is equal to this value, this value is equal to this value, and so on and so forth. You'll find this will be a symmetric matrices. You can also see it in another way, some linear algebra logic, that each column will be a linear combination of the column of u transpose. Okay, so I mean, you can say that whenever this happens, you can always write it like u1 into u, u2 into u, and so on. Right? You can always write it like this, and you can see each column vector is a multiple of the same vector u. So it has rank 1. So this matrix has rank 1, and this is also symmetric, as we saw earlier. So because this matrix has rank 1, this is called rank 1 correction. All right. So you just do it yourself, that you try to find u transpose, and you'll find that this is symmetric and rank 1. So now if this is bk symmetric and this is symmetric, their sum will also be a symmetric matrix. So bk plus 1 is symmetric. So that we have ensured here. Now we have to choose alpha such that bk plus 1 satisfies the quasi-Newton condition. So choose alpha and u both. So u is a vector, but we have to choose alpha and u such that this bk plus 1 satisfies quasi-Newton condition. So choose alpha and u such that bk plus 1 satisfies quasi-Newton condition. Alright, so what is the quasi-Newton condition? It is bk plus 1 gamma k is equal to delta k. So what is bk plus 1? It is bk plus alpha u transpose gamma k is equal to delta k. You can write here delta k minus, this can be written as alpha u transpose gamma k into u. Please note, because it is a so because it is associative, the vector multiplication, this can be written as you can multiply u transpose gamma k first, which will give you a real number u transpose gamma k, and u can still be a vector, so u, right? So this comes out, and you can first multiply these two to give a real number, and then u comes out. This equals to delta k minus bk gamma k. So what we can do is we can assume, so this so basically for we need to choose u and alpha in such a way that this equation should follow. So now this equation we can because this is one equation and we have several variables, we can choose it in many ways. One of the simplest ways is we choose this to be 1 and choose this u to be whole of this right side. So given bk gamma k delta k, we choose u to be this value delta k minus bk gamma k, and we choose alpha to be 1 upon u transpose gamma k. Please note, u transpose gamma k is a real number, so this is possible. So this is one of the ways in which we can choose alpha and u, which will ensure that bk satisfies the quasi-Newton condition. All right, but one question that still lingers on is, does choosing alpha and u in this manner guarantees bk plus 1 to be positive definite? So we have ensured that bk plus 1 is symmetric through choosing a structure of the equation like this. We have also ensured that bk plus 1 follows the quasi-Newton condition by choosing u and alpha in such a way like this. But does choosing u and alpha in this way ensure that bk plus 1 is positive definite, which is an essential requirement of Quasi-Newton condition? So this question still remains. We'll try to answer this question in our next lecture. We'll conclude today's lecture, and we'll continue with Quasi-Newton method in our next class. So today we concluded Newton's method. We discussed modified Newton's method. We we um, we also discussed trust region based method, and we started with Quasi-Newton condition, and we'll try to answer this question whether choosing alpha and u in this way ensures that bk plus 1 is positive definite in the next lecture. Till then, thank you.